Thank you. Well, in the first place, I'd like to thank the organizers for the invitation. It is a great, great honor to be here. My tribute to Jean-Pierre's deep and elegant mathematics, and as well to his commitment to the Institut Fourier. I was very lucky to be one of his students, and during my stay here, I had the possibility of meeting him many, many times, and equally important was the numerous academic brothers. I see many of them here this week. A little bit changed, but essentially the same. I learned a lot from them, and it was a wonderful big family here some time ago. Okay, now apparently life goes on, so let me explain to you a few things about the Bogomolov-Gieseker inequality. So to start with x omega x, so this is like in Henri's talk, a compact Kähler manifold. And then let's also consider a vector bundle E on X. Let's say that is a vector bundle, holomorphic, of course. Holomorphic vector bundle of rank R, okay, on X. So if E is slope stable with respect to this metric, if E is, let's say, omega x stable, then we have an important result. We have the theorem that there exists a metric, that's HE, a Hermite-Einstein metric on E, is to say, if we take the contraction with respect to omega x of the curvature form, so the contraction with respect to omega x of this form is the endomorphism of E, and then the Hermite-Einstein condition is that this is a multiple times the identity of E, right? So it's a famous result. Simhan-Seshrad in dimension 1, and then Donaldson for projective case, and finally Uhlenbeck and Yau in the setting of compact Kähler manifold. Okay. Now, as a consequence of that, again under this assumption, if we define the discriminant of E is simply 2 times R C2 of E minus R minus 1 C1 of E squared, then we have the Kobayashi-Lübke inequality. It follows that integral over x of this to form delta of E wedge omega x to the power n minus 2 is semi-positive, right? This is the Kobayashi-Lübke inequality, right? And then I remind you that if you take if H is a metric having this property, then this is pointwise. So if you compute this 2 form with respect to the Hermite-Einstein metric, then this is a pointwise inequality. Okay, so you don't have to integrate to reach semi-positivity. Okay, pointwise inequality, a very nice, beautiful exercise in differential geometry. So the aim of my lecture would be formulate, well, and prove a similar inequality inequality. Similar meaning like 1 here in singular setting. Okay. In singular setting. I'll come to the motivation for doing that a bit later. But now let's trace our steps back and see, well, what sort of inequalities in this spirit have been proved in some time ago. So of course, I will start with the famous Bogomolov-Gieseker inequality. So let me just write it BMY. If X is a surface of general type, then we have that 3 times C2 greater than C1 square. Okay. So yeah, if you replace E with a tangent, you will see that the numbers that you get here, this is better than what we have here, right? So if I understood correctly, so this was in the 80s by Miyaoka. So what happened is that throughout the history is that it was Antonius van de Ven who came up with 8 here instead of 3, but he conjectured the right number should be 3. And then after Van de Ven's paper, there was a chase of improving the numbers. And then Bogomolov did it with 4. And then the last laugh had Miyaoka, who proved Van de Ven conjecture. And it's what we learned today in school, this inequality here. Now, a differential geometric counterpart of this inequality would be as follows, so that the second result I would like to mention, if X admits a Kähler-Einstein metric, then, so now let's write it here like that, integral over X, so it's 2n plus 2 C2 of X minus n C1 of X square wedge omega x to the appropriate power. No, it's here not omega x, but lambda times C1 of X to the appropriate power n minus 2 is semi-positive, where so lambda is such that this 1-1 form is this 1-1 class is positive, right? And if the Kähler-Einstein metric is with lambda equals to 0, then you simply don't have this, and you can replace this term with any Kähler metric. Okay, so it's a positivity for C2. Guggenheimer-Yau inequality, which generalizes this, but of course the difference is that here you have general type, right? And here it's necessarily that the canonical is either ample, 0, or anti-ample. Okay. Now, I must say that this was my first encounter with this type of inequalities through Jean-Pierre's very nice notes. You can still find them on his webpage. Now, this is done by exploiting in a very tricky way the symmetries of the curvature tensor. And then when I first come to look at this sort of inequality, the curvature tensor seems like a legendary monster with many indices instead of many heads. But then after reading Jean-Pierre's paper, well, you feel like it's not that after all. And this is, yeah, it's always good to read Jean-Pierre's paper. Anyway, it's a very, very nice and ingenious proof. I encourage you to have a look. Now, this was generalized in many, many contexts, in many, many ways by many, many people. If X is projective, So those are many generalizations. I will not put some name on the blackboard because if I should do a thorough job, I will spend the rest of my hour doing that. And if by some mistake I forget somebody, I will instantly become his or hers mortal enemy. Let me just say that it's based on, so one of the main techniques here, well, of course there are many things involved, but the main technique here is that the use of hyperplane sections. Use of hyperplane sections plays a crucial role in this story, combined with the usual theorems in this setting, namely that stability or semi-stability stability is preserved by taking sufficiently general complete intersection, and then you reduce to the case of surfaces and you negotiate. Right. In dimension 2, things are, we feel like we understand something. Okay. So what I would talk about in what follows, it will be the following setup. So X, so the setup for the rest of the talk. We will have at hand X, which is a compact Kähler analytic space, dimension 3, and then we also assume that X is log terminal, and then from what Henri already told you, we can remove a finite number of points. So this was G, K, K, P. Sorry for the abbreviation. So a finite number of points, P, K. Inside X, let's call this set Z, such that X minus Z has only quotient singularities. Quotient singularities, and then, so let's call this set X0. Okay. Moreover, let's say that now we have our X. What we need is also something for E here, and then let's say that we take E to be, we replace E with a coherent reflexive sheaf. So it's a coherent sheaf, well, reflexive sheaf on X. This exists such that somehow it respects this structure, this geometric structure that we have here. That is to say, when we restrict F to X0, let me just write it like this. This is an orbifold vector bundle, which means exactly what you think. That is to say, when we take a local uniformization of some open subset in X, then you take the pullback of F restricted to some open path, and the pullback extends to an honest vector bundle. Okay, so this would be what it means. That. And then, so now in this setup, let me write a remark here. If by chance Z, that is to say the set of bad guys here, is empty, then X is a perfectly decent orbifold. So X is an orbifold. So in case f is stable, if f is, let's say, omega x stable, then the inequality of type 1, then 1 follows without too much headache. Like it's according to the usual slogans that for quotient singularities, things are as good as the smooth ones, so to speak. So the proof follows absolutely the same pattern. So if not, so now what I would like to do is to try to see what can we, with what should be the right replacement for this inequality here. It is understood. Yes, thank you very much. I forgot to mention. Yeah, this is a very important point. Thank you, Thomas. Always good to have you around. So, now, in general, so if not, so let's see what we can do. So, well, there exists. So I first want to replace omega x by an element in its cohomology class, which somehow vanishes near the set Z, and this is easy to do. This is actually one of the main reasons why we state and prove something in dimension 3. I'll come back to this eventually later. So there exists a phi, which is, let's say, I use Henri's notation, so phi equals to 1, phi in, let's say, C infinity of x. And then we have two neighborhoods, say Z inside omega 2 times included in omega prime. So those are open, small open subsets. Open subsets. And then such that, so omega x plus ddc of phi, this should be omega x in the complement of omega prime, and 0 on omega. Okay, you can simply cut local potential of omega x, and this would be our function phi near the bed points, right? So it looks strange because this is in the cohomology class of a Kähler metric, but then still it's true. This representative is 0 in a neighborhood of a point, right? It's not very expensive to get that. Fine. And then another piece of data here. So I said to you that this guy has a orbifold vector bundle structure. So then we can endow it with a metric, so HF. So this would be orbifold metric on F, let's say restricted to x minus omega, right? So this omega again contains the set Z, for which we ignore everything about the singularities, but then as soon as I remove it, we can construct a so-called orbifold metric thanks to this hypothesis here. And then now our delta, our discriminant, let's say of F and HF. So I define it as simply. So let's say, what are the numbers? So it will be 2 times r theta 2 of FHF minus r minus 1 theta 1 of FHF. So where the thetas here are the Chern-Weil representatives for the Chern classes of F, right? So I take here, as Thomas said, so we take the so-called orbifold Chern classes, but it's only on this open part of X, okay? Still, we can still consider the integral over X, let's say regular of this 2-2 form, delta of F and wedge omega x. Now, if I stop here, I don't know what I'm talking about because this is only defined in the complement of omega. But then if I add ddc of phi, this is a perfectly well-defined 3 form on x regular, which I can integrate, and it will give me a number, right? So this is the analog of the inequality we have here, but in this context in which we have a big open subset on which we have singularities we understand, and then some set of points on which we understand nothing. Fine, and then the question was, so it was conjectured by Campana, Hörling, and Peternel that actually if f is stable, then this quantity should be semi-positive. And this is the main theorem I would like to explain today. So the theorem is that, let's say, call this I. Assume that f is stable, omega x stable, then I is semi-positive. Okay, so the motivation for this question comes from Thomas' long-term project of implementing, of running a minimal model program in the Kähler setting. And then this statement comes into the picture while trying to prove the abundance conjecture in the 3 in the Kähler setting. Fine, so this is the statement. And then for the rest of the proof, for the rest of the talk, I will try to explain to you the main steps of the proof. But then do you have some questions before I'm doing it? Yes, please.
What is the state of the art
I think you will see it in the proof. Yeah. Yes, precisely. So I forgot to mention, thank you very much for the very good question. So if you change here the number of points or this function or this metric, provided that it's orbifold where it should, then the number that you get here is the same. Those are, again, here we compute the so-called orbifold Chern classes for this guy. Okay. Unfortunately not. That's part of the difficulty. But you will see if you survive until the end. Yeah, I hope so too. Fine. So let's go ahead and see what's inside here. So the step 1. So the rest of the proof, rest of the talk. Yeah. Rest of the talk. So let's see main steps in the proof. So let's say step 1. First, I will somehow construct a metric which will be adapted for our next needs. So it will be an interpolation metric. What do I mean by that? So I will simply write it first and then explain what's inside there. So this would be a big constant times omega x plus the Hessian of let's say 1 minus theta square phi orb plus theta square phi, let's say z, phi p, I'm sorry. Okay, where here, let's say theta equals to 1 in omega, well, in omega is 0 in omega prime, well, no, 0 on x minus omega prime, and then phi orb is a function defined in the complement of omega, such that omega x plus ddc of phi orb for singularities on x minus omega. Okay, so we can construct such a function phi orb in such a way that well, again, up to multiplying this one with the constant, we get orbifold singularities outside some open subset of the set Z. So now, if you look at this omega theta here, okay, and phi p, ddc of phi p is omega x near Z. Okay, so I take the local potentials of my method and I put them together, and this would be my phi p. And since I'm taking this cutoff function, well, I didn't say, but you understood, those open subsets should be small, right? Containing the, so we have here x pi embedding in some Cn, 0, and then they should be localized near this. Now, exactly. C and the square here, they are just taking care of the cutoff function. Yeah, so I think, yeah, it was my colleague Thomas Peternel who asked me this question some time ago. When I saw it like that, I said, okay, this afternoon I'm busy, I have to teach, but then by tomorrow it will be done. It was a gross misunderstanding of the difficulties, because somehow, you see, here, we again, so this metric is only defined on some open sets, so you don't know how to integrate by parts. And this is somehow what I'm trying to suggest here, that this metric should somehow should have a twofold role. It should be smooth enough near the set Z, and then should have the expected singularities outside some open set here. Okay, that's exactly somehow the motivation for constructing such a twisted object. Yeah. And then, so let's move this one up. And then here, what is the main thing about? So main property of this x reg and omega theta. So the proposition, so the last proposition in Aristotle, Exposé. I even forgot my French. Huh? Exposé still holds true. Okay, so even if the metric is, like I said, a bit over twisted, the results that already mentioned, the GPSS, right? Guofeng, Song, and Sturm, they are extremely robust, and then they allow us to prove that the same kind of result in this case. Okay, despite of the singularities, despite of the fact that this metric looks kind of hopeless, right? Because it's quasi-arithmetic to 1 minus theta square omega orb plus theta square omega x, right? So yeah, if you have, for example, Sobolev inequalities for two metrics, it's not clear that Sobolev still holds for the convex combination and so on. Anyway, the geometric invariants that one need in this kind of thing are under control thanks to this work, these people's work. Now let's move on to step 2. Is that now I have a metric. What I want is a substitute for the Hermite-Einstein metric on F. So let's look at it like that. So F is a coherent, for any coherent and torsion-free sheaf on X, we can do the following construction. So let's take U inside X, small enough open subset. And then, so we have such that F is given by the following resolution. The structural sheaf to the power P goes to the 1 to the power Q, goes to F, restricted to U, goes to 0. Okay. Now, this holds for every U. Now I can endow this, which is just a trivial vector bundle of rank Q with the trivial metric. And then I say that age F0, so this is a quotient metric on F. That's F restricted to X minus sigma. I'll tell you in a second who's sigma here, induced by this short exact sequences plus, of course, partition of unity. Okay, so sigma is X singular union F singular. That is to say, the restriction of F in the complement of sigma, it's in particular a vector bundle. Okay, so if you look, if you remember, of course you do, how we teach the students that we construct a metric on a holomorphic vector bundle, we trivialize it locally, and locally we have a metric, and then we take a partition of unit. So here we don't have such a nice picture, but the next best thing is to use this local resolution of F together with the unique metric, right, given as a quotient, right, here. This one exists, it's perfectly well defined, where F is a vector bundle, and it has very, very nice properties, which unfortunately I don't have time to mention now. So this is our somehow background metric on a coherent torsion-free sheaf. Torsion-free because this one should have codimension at least 2. And then so yeah, in many papers, for example, the one of Professor Takayama here, one can be more liberal to say that a metric for F is simply any Hermitian metric in the complement of this sigma. Here I want something more dictatorial, I don't know, something more, a bit more precise. For reasons I will try to hint a little bit later. Fine, so with this sigma, we denote by, let's say, phi sigma. Well, okay, maybe. Phi sigma here is a function which locally looks like log of sum of fj square, where fj is a local generators for sigma, right? So we take a function with logarithmic poles. Minus infinity is that is exactly sigma. So fj is the generators. So equations for our set sigma. And then the result I would like to mention, which answer the chairman's question, is the following. Now here there are many authors, so I'll just mention, I'll just write it C++. So C is for Sao, then Philip Naumann, Patrick Graf, Xiaojun Wu, Thomas Pettenel, and your humble narrator. So what is the statement? So the assumptions on F are as above. But then if assume moreover that F is omega x stable, then there exists a metric, let's say like this, hf. So is hf0 the one constructed there, composed with the exponential of some endomorphism? So it's a metric in the usual sense on x, on f restricted to x minus z, x minus sigma, I'm sorry, but with the following properties. So this metric, so let's write it like this. So hf satisfies the Hermite-Einstein equation with respect to omega theta. So with respect to this over-twisted metric here that we constructed before. And, what else? Moreover, hf is the orbifold metric where omega theta is, that is to say, let's say on x minus omega. Okay, so x minus omega, just a second. Let's play safely, say x minus omega prime, bigger one. And moreover, we know, even if the bounds are bad, but there are some bounds, so that is to say, the exponential of s. So this endomorphism of f restricted to x0, which makes the difference between the metric we fix and the Hermite-Einstein metric, well, it's bounded by what? Some constant times the identity of f restricted to x0, and the lower bound is, let's say, c minus 1 times the exponential of n times this function that I can vanish. Phi z times the identity. Okay. So this is true on, so pointwise on x0. Okay, so that is to say, this constant and the number here doesn't get worse as you go closer and closer to the singularity. Okay, so like I said, this is more or less the dream estimates, right? So in the sense that the metric that you construct is comparable to the one you start with, but then again, this lower bound is right, so it has zeros around on z. In general, and these efforts we couldn't do better than that. Fine. So maybe a few comments about the proof of this result. So about the proof. Now there are two main ingredients. The first one is the classical stability theory. And the second one is, once again, GPS. So somehow, yeah, classical, well, people use classical in a rather loose sense. Generally, it means that the question was proved before their PhD. Now, I'm not an exception, so what I mean is all that you need in order to understand the proof, if you want, is the papers by Simpson, and a book by Yum Tong Siu. Right, so it's nothing really very recent. And why do we have to combine these? Well, in the first place, the proof we have here a modification of x. This one is smooth. The modular torsion is honest vector boundary on the space X. So this is a very nice and important result of Rossi. And then, so of course, what you want to do is to say that fine, I take so the stability condition is somehow stable. Well, stable. You conserve this by small perturbations. So then you take simply pi upper star of omega theta, and this one you write it up there as limit, let's say omega k, like this, where those are honest Kähler metrics. E will be stable with respect to omega k as soon as k is large enough. So for now we are back to Uhlenbeck-Yau theorem. It's enough to take the hk is the Hermite-Einstein metric on E and take the limit. Simple, isn't it? Well, of course, the thing is that in order to understand those objects here, you need a lot of geometric information about the metric omega k. And this is exactly what these guys provide. That even if many geometric invariants are not bounded, for example, Ricci curvature is one of the important absent in the story. Nevertheless, the recent progress here allow us to somehow understand well enough this family of metrics and ultimately obtain the result. Okay, that's somehow how we do it. In any case, as I think everybody knows, as soon as you have some singular space, you only have two choices, right? Either you know something about the singularities in a very, very precise manner, and then you have a model for the objects that you want to obtain. And then you try very hard to say that the object that you construct is the same as the model, right? So if you know beforehand something about the singularities of this guy, then things are getting better because somehow you know what to expect, which functional spaces you should consider, and so forth. Or take the epsilons. So then, well, epsilon is 1 over k. I'll proceed by approximation like this and hope that you will somehow get convergence. Usually, the second method is much more, well, risky, so to speak. Again, because of the many of the geometric invariants of the approximating sequence here. Fine. So now let's look again at what we want to prove. So which is up there, and then so I will draw the same pictures as Henri, but maybe less inspired. So this is omega, right? So this is omega prime. So somehow here I am a happy man. We understand everything about metric, right? This orbifold metric, I can use it to compute this discriminant delta. But then here, it's really a problem, right? So given how the metric behaves, right? So somehow the fact that this one has orbifold singularities combined with the equation of that we have, this one tells you that here you will get the orbifold metric, orbifold structure for HF for free as soon as this is satisfied. But then things are very different here, right? Because this metric doesn't have orbifold singularities any longer. Fine. So let's look what we are doing next. Step 3. So let's look how the time looks like. Well, looks bad. So Now let's consider local uniformization. So local uniformization for x and let's say some point c0 here. I assume that this is, as in Aristotle, like S, let's say 0 times c0, because here we are in dimension 3. So this is orbifold singularities of in dimension 2 times c, right? So we put ourselves near one of these points. So you have to imagine that. So this is my point P, which I don't touch, but the z0 here is outside. So I do have this local uniformization. And then so we have a vector bundle, let's say E on V. So that's a vector bundle such that E is the same isomorphic with pi star of F restricted to U0. So let's say U minus sigma. So this one is a vector bundle. So and then this one we have to restrict it on V minus W, where W is none other than the inverse image of this. So P minus 1 of 0 times C0. Okay, codimension 2, you can think of it like vanishing of W1 is 0, W2 is 0, right? So because of the orbifold structure, we have such vector bundle. And then now let's look a little bit at the P star of HF. Again, restricted here. I will not write it because of the time I'm running out of time. So let's say that this is our HE. Okay. And then the claim is that, even if I don't know that this one is a honest smooth metric anymore, at least it's quasi-isometric to 1. So exists a constant. Such that C times, of course, this constant, you understand, depends on the closer we get to the bed point, the worse is the constant. But OK, let's say we don't care about it now. So minus 1 times H naught is less than HE is less than C naught. So it's simply a smooth metric on E. Okay. So even if this one we don't know that is honest smooth metric for E, which would have mean that HF is an orbifold metric here too, right? We know at least that is comparable with the smooth metric in this sense, in this way. And then so here, just to see why we need all those, where does the proposition already mentioned into the picture? For example, here, so let's say if we take eta, so it's the local holomorphic section on E of, well, E is the beautifully, right? Of E. And then what we want to understand is the norm of eta with respect to HE, right? With respect to the pullback of this guy here. Let's say square to make it more beautiful. So now, if I'm able to show that this is bounded by some constant depending on E, depending on V. But anyways, if I'm able to some constant depending on eta I wanted to mention, then at least this will show this, right? The problem is that again, this is only defined in the complement of W, all right? So according to a very, very good principle, if you don't know, if you want to estimate something, take the Laplacian. That's exactly what we do here. So, but maybe for you to understand the story, so if we take DDC of this, of the log of this, well, so this has two parts. One which is positive and we skip. And then there is the curvature of the E star eta eta divided by norm of eta square, right? That's what we learn. So maybe I put here minus, and then the curvature of E. And then when we take the trace with respect to the pullback of the metric, so then delta pi upper star of omega theta of the log of square well, here something very, very nice is happening is that the Laplace with respect to a Kähler metric is simply we contract this 1-1 form with respect to the metric, right? And for that contraction, we already know that is a multiple of the identity. So it will be greater than some constant, which is universal. Doesn't depend, doesn't get worse when I am getting close to the points. And then, well, so you do something, so there are quite a few calculations here. But then the outcome is that the Laplace with respect to p upper star of omega theta of, let's say, chi times norm of eta to the power 2 times epsilon will be greater than minus a constant times chi tilde eta to the power 2 times epsilon. Okay, so this is, again, only true on v minus w. Okay, so chi is the cutoff function, so that, yeah, this vanishes in the neighborhood of the boundary of v. Okay, so we have this pointwise inequality, right? Usually we're in trouble with these inequalities because, yeah, you have to use something about the function here. And again, by the proposition that Henri mentioned, this would be bounded from above, okay? And then you use the same for the dual of E, so it is still Hermite-Einstein, and then you get the other inequality, okay? But here is what somehow the heart of the matter, with epsilon small enough, this one we can make this as integrable as we want. Fine. Now let's try to move this one up. I said up. So I still said up. Yeah. Okay, so my time is almost over, so let me just make it short. So what's happening here, in probably the most technical step of the proof, is that is the following. So let's say step 4 is that this current delta of f hf is closed in the following sense. The integral over x regular of the delta of f hf wedge d bar of tau is 0 for any tau is 1-0 form with the support is in x minus z, so outside the finite set of points. So we know how to integrate this, and the result is as we expect, provided that the supremum on x regular of the norm of theta with respect to norm of tau omega theta plus the norm of the d bar tau is finite. Okay, so this is why I put closed in the quotation marks, because you can only write this for such thetas which verify this L infinity bound here. So yeah, so I cannot explain this to you, but just say that it's a consequence of the step 3, which doesn't come as a surprise, right? Plus the fact, plus many calculations. You can have a look. And then end of the proof. Well, it looks as you expect. So integral over x regular of the delta of f hf. So I have to couple this with omega x plus ddc of phi. But then now I want to use the fact that we have at hand a Einstein metric. So then in the first place, what I can do is to take a family of cutoff functions here, which so chi epsilon converges to the identity function of x minus z. Right, so it's 1 almost everywhere, and 0 in the complement of this finite set of points, which give us such a big trouble. Then I can write this like the integral of x regular of chi epsilon delta of f hf wedge omega theta. Well, let's say it's equivalent. Wedge omega theta plus the leftover chi epsilon delta of f hf. And then what we see is that this one and this one are virtually the same modulo ddc of, let's say, well, the factor that I have there, 1 minus theta square phi orbifold plus theta square phi p. And then so here is why we need a step 4 is simply to say that this is the same as this one by step 4 by d of chi epsilon wedge dc of the rest. Okay, so this is somehow what we ignore. Again, because, in general, again, because the HF is only smooth here. We don't know what's happening at the boundary to somehow get rid of the boundary term if you want. Now, something really nice is happening is that this chi epsilon, you can think of it like the log 1 over norm of z square. So I'm now. Then the other one is phi p is the O of z square. So if you look how these two behaves when you couple them like this, then you will see, you will have the very pleasant surprise to see that this one is L infinity bound and the support is very, very small, right? Because I'm taking the derivative of the cutoff function. So it is somehow this O of z square which compensates the way the cutoff function here blows up. And then together with the well, now things are really getting seriously better because I'm integrating something in L1 on a domain which is smaller and smaller, so it doesn't have any other alternative than converging to 0. So we get rid of the boundary term like that. So we are left with this, which, as I already told you, is a pointwise inequality. So multiplying it with this positive function doesn't bother us, so it's a semi-positive. And that's the end of the proof and the end of my talk. Thank you very much.